Hello, pre-calc. So the top part of this chart is already filled out because that's what you're supposed to do with Desmos to uncover that. So then we notice whatever your degree is, that the number of turnarounds, which means max and minimum values, should be one less. So how are the degree and number turning? The number of turning points is always at least one less than n, the degree of your function. Okay, which is a nice way to figure out what the potential degree is. And then in terms of the n behavior, if your leading coefficient is negative and it's an odd function, your branches are going to go in opposite directions. So with a negative, as you are going to positive infinity, your graph will be going down. As you are going to a negative infinity, your graph will be going up. So this is a positive infinity, this would be a negative infinity. So it goes in opposite directions. If you also have an odd function, but your leading coefficient is positive, in that case, you're going to be going up at the end, but you started from down below. And then we can connect these in between any way you want. So we have that this one will be a positive infinity, and this will be a negative infinity. So when you have a positive coefficient, you end in a positive direction. Now with the even, the nice thing about them, they will always go in the same direction on the endpoints. So if I have, move this over a little bit, if I have this is even and it's a negative lead coefficient, then both of your endpoints, you can do whatever you want in between, will be going to a negative infinity. And if it is a positive lead coefficient, then you will be ending going to a positive. Now, you can also abbreviate these ones. I can say the limit as x goes to both positive and negative infinity equals positive infinity. And we don't tend to write the plus. I'm just kind of emphasizing that fact. Okay, so one of the things you notice as we often cross the x-axis, we want to find what those values are. So if I give you a polynomial, and you want to find the zeros, we're going to do that routine you did in Algebra 2, where you look at the factors of the lead coefficient and your constant. So P represents the constant, and Q represents the lead coefficient. Now in this case, our lead coefficient is 1, so this makes this a little nice. So what we're going to do is we're going to try and find our first 0 by plugging in values. So I plug in a 1, and I find that if I plug in 1, I am not going to get 0. I don't care what I get, I'm just looking for a 0. So now I'm going to plug in, usually I would plug in a negative 1, but I'm going to kind of lead us here quickly. I just want to show you the process. So f of 2, if I plug that in, I won't get a 0. If I plug in 3, I do get a 0. So that's nice. That tells me that x minus 3 is one of the factors of my equation. So I'm going to synthetically divide 3 into the equation. So I write down the coefficients of x cubed, of x squared, of x, and of my constant. Now if I was missing a power, remember you have to put in a placeholder. So do not forget those placeholders. Then the process is you always bring down that first lead coefficient. So I'm going to bring down the 1, and we always multiply against who's in the box, the 3. So 3 times 1 is 3, and then we add. 3 minus 1 is 2. 3 times 2 is 6, and we add. 5 times 3, whoops, something didn't happen. I did something wrong. Oh, that was a negative 10. Hello, I can add. I was like, wait, this is supposed to be 0. There's a good indication if you make a mistake. So negative 10 plus 6 is a negative 4. 4 times 3 is a negative 12. That's what we wanted. We wanted that 0 at the end. And now we have what's called a depressed polynomial. I love that term. So we started with third degree. So that means this is now the coefficients of a second degree. So this would be 1x squared plus 2x minus 4. And in this case, that is not factorable. So to find my other zeros, I'm going to do completing the square on this because I prefer that to, I actually prefer completing the square to the quadratic formula. So this is going to be x squared plus 2x plus blank equals 4 plus blank. I'm going to add 1/2 of 2 squared, add that to both sides. So that becomes x plus 1 squared equals 5. And we take the square root with the plus or minus. So x plus 1 plus or minus square root of 5. So x equals negative 1 plus or minus rad 5, as well as our original. So there's our 3 roots because we had a cubic. But I did want to review that synthetic with you. So on this page, again, you can use Desmos or synthetic to find that first 0. And so if you do this on Desmos, you would find you'd have a graph that looks something like this. So it crossed at a negative 2, at a positive 1, and at a positive 5. You had a y-intercept down here at negative 10. So I know my zeros are x equals negative 2, positive 1, and 5, which makes sense. You have 3 zeros, and it is a cubic. If I'm going to write it in factored form, I have to acknowledge that my lead coefficient is still a negative 1. So I'm going to keep that there and write x minus a negative 2, x minus 1, x minus 5. That would be my factored form. Now on this next one, if I were to graph that, you would notice it looks something like this. It has a lot of symmetry. And so this is at negative 3, this is at negative 1, this is at 1, this is at a positive 3, and you cross here at 9. So my zeros are plus or minus 1 and plus or minus 3. So when I write it in factored form, I'm actually going to take that shortcut and write it as plus or minus. Whoops, forgot the 3. That's good enough. All right, this next example is the one that we had just done on the previous page. So we know that we have only one real zero, and we know that our other rational, they weren't complex, I don't think. I'm going to look back at that. No, it wasn't complex. It was, because that's the same equation, it was rational. So we had x equals, what was it? Going back there, negative 1 plus or minus rad 5. And so sketching that graph, you'll still have your 2 roots. One will be at a positive 3. One is going to be at, this one would be the negative 1 minus rad 5. This one will be the negative 1 plus rad 5. So sketch a graph and behavior and the roots. And we already did the synthetic and everything on the other. Okay, now we get down here. We are given a cubic equation. Determine the following behavior based on the degree and the lead coefficient. So we know that we have a positive lead and it is an odd function. So given that it's an odd function, I know that I'm going to be having something along like that. Positive at the very end, negative at the beginning. So as x is going to negative infinity, that's going to negative. As x is going to a positive infinity, y is going to a positive infinity. And in this case, your maximum number of zeros would be 3 because it is cubic. Now we don't know in particular, that's just the maximum number. Remember, they always come in, if you have complex roots, they will always come in conjugate pairs. So you can either have one real root, 3 real roots, 5 real roots. The other 2 would have to be the complex. So they want us to graph this polynomial and identify the one integer root. So we can, again, if you graph it on Desmos, we can see that -2 is going to be the one real root. So the graph itself from Desmos is going to look something along that as a sketch. So I'm going to synthetically divide -2 into this. So this will be 2, 7, 8, 4. Again, we didn't have any missing powers, but if I did, I'd have to leave that 0. So I always bring down my first lead coefficient. -2 times 2 is a -4. 7 minus 4 is 3. 3 times a -2 is a -6. That gives me a sum of 2. And again, -4, you expect to get a 0 there. So 2x squared plus 3x plus 2 is the remaining quadratic. And to find the roots there, now I am going to use the quadratic formula, where a is 2, b is 3, c is 2. I always do this first. We know it, expect it to be negative. So 9 minus 4 times 2 times 2. So 9 minus 16 is a -7. So x equals opposite of b over 2 times a, plus or minus the square root of -7 over 2 times a, and simplifying that is -3/4 plus or minus I rad 7. So there are your 2 complex roots, which again, they always come in complex conjugate, and that represents one of your turnarounds. All right, so this last one, find the zeros and the factored form. So on this one, let's see, we could do a quick Desmos, or we could do the a over b, which I guess, oh, I think I was supposed to do that on the last ones too. All right, I'll do it appropriately on this one. It does take longer, but that's okay. So we know that at f of 1, if I plug in 1 plus 4 is 5, minus 3 is 2, that will not equal 0. All right, let's try f of 2. And I should really try -1, but I'm going to check this. So 8 plus 16 is 24. Minus 6 is 18, minus 18, that does give me 0. So I know that x minus 2 will be one of the factors. So let me find the others. So 2 goes into 1, we have a 4. Again, no missing coefficients. And now I'm going to bring down the 1, that's a 2, 6, 12, minus 3 is 9. That gives me a positive 18, and this is a perfect square that is left behind. So that gave me x squared plus 6x plus 9, which factors very nicely. So this is a good example to show that I know I'm going to cross at a positive 2, and I know that I'm going to bounce, so you have 2 roots at -3. I know that my lead coefficient is positive, so I'm going here, but then I know because it's odd, this has to be going in this direction. So what's going to happen is whenever you have 2 roots, you bounce at that particular intercept. Okay? Okay, so now we're going to look at what happens when you have those repeating decimals. So I notice here I have a 4th degree, just looking at the x's, and my lead coefficient is positive. My zeros will be at 0. I will bounce there at a positive 2 and a -3. So we want to label those. I know that I'm going to be positive at both ends because it's even. So I want to come through 3, I'm going to bounce at 0, and then turn around and go up. All right, so you bounce whenever you have a double, a multiplicity of 2. Here I'm also quartic, but with a negative lead coefficient. My zeros will be at a positive 4 and a negative 3. And I'm going to bounce at both. So I'm going to come up, bounce, and I should be going down on both endpoints. And now this next one, notice I have a 0, so this is a 5th degree with a negative lead coefficient. So I'm going to be ending going down. Let's see, my zeros, I'll have a plateau at 0. 1, 2, 3, 4, negative 5. I will have a 0, and at a positive 2. I know my scale's not great, but you get the idea. So I have to be coming down at the end and coming from up high because it's odd, so opposite direction. So I'm going to come down. Then when I hit 0, I plateau, meaning you just kind of go flat for an instant, and then it comes, I did not mean to go through. Let me just erase this last little bit. I needed to just have a little plateau, and then it just keeps going up and turns around to go back down. So this right here is called a plateau. So it just kind of levels out for an instant. Okay, now down below we have the remainder factor theorem. So basically what this is saying is if I just plug in g of 3, so when I plug it in, I get 37. Now, if I bother to go through and do the synthetic division, so I have the 1, the 2, the negative 3, the 1, you bring this down, you got the 3, that's 5, that's 15, that's 12, that's 15. I did something wrong. That's 12 times 3. Oh, 12 times 3, hello, is 36. I can multiply, right? I'm just going to write over this. 36. Notice I get the same remainder as if I just pull it in. So g of 3 equals the remainder from synthetic division. And that is always going to be the case. That's why it's faster just to plug in a number if you're looking for zeros rather than doing the synthetic division first. So if I plug in a g of negative 1, you get negative 1 minus 1, negative 2 plus 10, which is 8. 8 minus 8 is 0. And if I do my synthetic division, so this is a nice check, you should, negative 1, negative 10, negative 8, you know you expect to get a remainder of, sorry, it's hard to talk and write at the same time. You should get a remainder of 0. That's what we expect. So that means I can now factor this into x plus 1. And then this is, I'm going to have to do it over here. This is x squared minus 2x minus 8. That is actually factorable into x minus 4x plus 2. So you have the full, I'm running out of room, factorization of that polynomial, which is kind of cool just by doing a little synthetic division and substituting for a 0. So what you did in part A above is called direct substitution, is when you just plug in directly. Synthetic substitution is when you're doing that synthetic division. So to show that something is a factor, you're wanting to get a remainder of 0. So what I would do with that, and again, we don't have, it's kind of the same concept, but I'll just go through this quickly. It means that f of 8 equals 0, so I can just divide this. So this is a 1, negative 4, negative 29, negative 24. Bring down the 1, that's 8, that's going to be 4, 32, that's going to be 3, and notice we did get a 0, so x squared plus 4x plus 3 factors into x plus 3, x plus 1, and from before x minus 8. So that would be your full factorization. All right, that is called the remainder theorem, that if you just plug in a value, whatever you get is the same as if you had done the synthetic division. Okay? Okay, so now if we give you a graph, we want you to identify the possible degree. So there's two ways to do this. 1, 2, 3, 4, 5. I notice I cross at 5 places, so it is at least 5th degree. But I'm going to double check. 1, 2, 3, 4 turnarounds also tells me that it's probably at least a 5th degree. Sometimes there's zeros you don't see. And then leading coefficient is going to be positive, and that's because of the final, what's happening over on the right side. Number of real zeros, in this case, we crossed 5 times, so I will say that there will be, I didn't need to say 5th, just there will be 5 zeros because that's how many times you actually cross. Each one of these is a 0. And the number of complex, in this case, it would be none. You didn't have any turnarounds off the axis. These two should add up to the degree. The number of real plus the number of complex, which should always be either 0, 2, 4, because it has to come in complex conjugates. So 5 plus 0 is 5. So again, we know this from Algebra 2 that, you know, wherever you have a maximum, that changes. So you are going down here, you're going down here, I am increasing here, and your extremes are at your turnarounds, basically. So then we have this check for understanding. This is for you to do on your own. So you should probably turn off the video, but after you've done it, I will go ahead and fill this out just so you can double check. So on number 1, we know it's odd because it's going in opposite directions. You are going to positive infinity at the end, and you are going to negative infinity at the beginning. You have 1, 2, 3, 4, 5 real zeros. It looks like there's no 1, 2, 3, so you had 4 turnarounds. So 5 plus 0 would add up to the 5 that one probably is at. And this one, it's going to be even, and you're going down in both. These are both going down. And then you have 2 real zeros, and it looks like you then would have 2 complex, because this looks like it would be a 4th degree since you have 3 turnarounds. Down here, you can have lots of, when you're sketching, there's many variations. This is my own. I know I have a 5th degree with a positive lead coefficient, so that means it's going to have to be like this. 3 real roots and 2 imaginary. So I want to cross 3 times, and then I'll have a turnaround off. So I still have 4 turnarounds, notice, which makes it 5th degree, but there's only crossing at 3 times. Okay, and then this next one, 4th degree, I'm going to have to just put this in here. You have your 2 crosses, you're all positive, and this last one, you don't cross at all. Okay, I hope that helped.